Okay, here's another one in our session of videos to help us to be able to do flip learning, and also help us to get things finished. And also it's good for you because you can then stop and pause as we go through. So I'm going to share this window with you, okay? And as per usual, you can see that we have got homework, which is obviously you should be trying to do a past paper a week now. Obviously, we're finishing off the physical chemistry, so there may be some questions on physical paper questions that you can't do yet. Okay, so we've got the 2 topics to go. Okay, 23, 24. Okay, and a reminder of the workshops between 1 and 2 on a Monday and Tuesday. So in the last topic, as a quick recap and a quick starter, you can have a go at this calculation here. So you are being asked to work out delta H, delta S, and then delta G, and obviously possibly any comments. So what you should do is stop the video and carry on when ready. Okay, so let's have a look at the answers. So here are the answers. Delta H is the formation of the products minus the formation of the reactants. Put those in, we get that number. Delta S is the sum of the entropies of the products minus the sum of the entropy of the reactants. We get that number, okay? And then delta G, the Gibbs free energy, is delta H minus T delta S. And so if we put that in, we get minus 92.22, etc. Okay, and so the delta G is minus 32.99, which means that the reaction is feasible and should go ahead. Okay, right, and this is at 298. We're at 298, yeah, so 25 degrees Celsius. So here is the working out of that. So and this is showing that both the enthalpy and the X is exothermic and the entropy changes are negative. Then there is going to be a temperature point at which this reaction happens, and a temperature point below which the reaction doesn't happen. Becomes more feasible as delta G becomes positive, and less feasible as delta G, more feasible as delta G is negative, and less feasible as delta G becomes positive. And delta G is going to become positive at higher temperature values. Okay. So there's a summary of that feasibility table, okay, which you can have a look at, and obviously you should have written down from the last lesson. So we're going to move on to redox reactions. So we have done redox before, so here are the key points, okay, and we'll go through those. Okay, and we should be able to construct some redox equations, which we'll be going through. So keywords are those. Obviously, some of those, well, all of those words you've come across before. It should just be a recap. Okay, so obviously you should have flashcards of those so you can actually quote those as per those definitions. If you can quote them as those definitions, if they ask you, then you'll get it right. Okay, we are nearly there. Okay, so we have done in module 5 rates or kinetics, equilibrium, bases and buffers, enthalpy, entropy, and free energy, which is it's commonly called thermodynamics. So we're now doing electrochemistry, and it's going to overlap with a lot of these topics here. So the father of electrochemistry is Michael Faraday, who has a nice museum in central London, and he had pretty humble beginnings. Okay, he was an apprentice to Humphrey Davy, okay, who discovered that acids don't all contain oxygen. And Faraday invented the first electric motor. He coined the terms electrode and ion. He came up with the 2 laws of electrochemistry, so that the amount of substance that you get on an electrode is dependent on the amount of electricity passed through it. And it's in the ratio of their chemical equivalent rate. So quite a lot of stuff that he was doing. Hence, he has quite an impressive museum in London. So, excuse me. So we're going to need to have some revision of oxidation numbers. So what are the rules of oxidation numbers? Now, hopefully I can get a little sign up. That will come up here. And you should probably now try and work out what the rules for oxidation numbers are. So stop the video and carry on when ready. Okay, so how many could you remember? So you should then be able to use these rules to follow or prove that those reactions are redox reactions, okay? And then evaluate your rules. Have the rules that you've written been good enough to actually classify those reactions as redox reactions? And have they been able to identify what's oxidized, what's reduced, and if there's anything missing, we can have a look at those. Okay, so you should now try and do those questions. Okay, so again, you should stop the video, carry on when ready. So write out or work out what's happening there in terms of redox, what the oxidation numbers are. Stop the video, carry on when ready. Okay, so let's go through the answers. So we've got that the iron as a solid and as an element is 0. The hydrogen in H2SO4 is H+, because it's the hydrogen ion, so we have an acid. In iron sulfate, we've got iron 2 sulfate, so the iron is iron +2, and the hydrogen that's been made is now 0. So the iron has been oxidized, it's gone from 0 to +2, so in oxidation you'll get more positive. And the H2 in sulfuric acid, which was +1, has been reduced. Okay, so the number's gone down from +1 to 0. Okay, and iron has lost 2 electrons to become +2. And each hydrogen has gained 1 electron, but there's 2 of them, hence it is balanced. Okay, the next one. Okay, so in that case, the sulfur dioxide, oxygen is -2, therefore the sulfur must be +4. The vanadium oxide or vanadium pentoxide, again, oxygen is -2, making -10 because there's 5 of them. It's 2 vanadiums, so it must be V2O5. And you've got the other numbers on there. So now we can have a look and see what they've done. So the sulfur has been oxidized, gone from +4 to +6. They've lost 2, each one's lost, or there's only one sulfur, it's lost 2 electrons. And the vanadium has been reduced from +4 to +5 to +4, gaining an electron, and there's 2 of them. And again, because there's 2, that makes 2 electrons, that balances the 2 electrons from the sulfur. Okay, so here is the last one, the manganese system, and manganese iron. Okay, manganese has gone from +7 to +2, it's gained 5 electrons, and the iron has gone from +2 to +3, so it's lost 1 electron. So there's 5 of them that have done that, so that gives you 5 electrons to give to the manganese. Okay, so let's have a look at those rules. Hopefully your rules look something like this. All atoms in elements have oxidation state 0. Metals are positive up to the number of their electrons in their outer shell. Okay, non-metals are mostly negative, but can be positive up to the number of electrons in their outer shell. Oxidation states of atoms in a compound add up to 0. Oxidation state of atoms in an ion add up to the charge of the ion. So this is the specific table that you should be learning. Okay, so if I put these all up, okay, now the technique for learning these, okay, is to copy it out, cover it, check, copy it out, cover it, do it again, check you got it right. Keep doing that until you have got it right. So if you need to, you should now stop the video and copy out the table just so that you have it again. And the more times you do it, the better it will stick into your memory, the easier it will be to retrieve it from your memory. And retrieval is the key. Okay, so the funny ones are oxygen, always -2 except as a peroxide. Okay, so pop that down there and let's get a pen up. So peroxide, okay, is something where you've got oxygen joined to oxygen, like hydrogen peroxide, which I'm now drawing on the screen. So there is hydrogen peroxide. Okay, also in compounds with F, because F is more electronegative than oxygen, so it will hold on to its electrons and grab them from oxygen. Okay, chlorine is -1 except when it's with fluorine and oxygen, where it has positive values, and it can be positive up to the number of electrons in its shell, so it can be up to +7, because 7 electrons is outer shell. Excuse me. Right. So now we need to get to how can we name some of these compounds, because we need to have this idea of the Roman numeral, which we have done before. Manganese 4 oxide. So I'll go through this really quickly. It means that the manganese is +4. So therefore manganese 4 oxide is MnO2. Oxygen gives us 4-. The manganese is +4, so that compound is 0, following our rules. Dichromate 2-. Dichromate 6. The chromium must be +6. Okay, so 2 plus 6s makes plus 12. Oxygen is minus 2, 7 of them, minus 14, leaving us an overall charge of 2 minus. Okay, so the chromium is in the plus 6 oxidation state. Now, formula of sulfur 6 oxide, okay, is SO3. Okay, and the reason for that is oxygen is minus 2, it's sulfur 6, so it's 6 plus for the sulfur and 2 minus for the oxygen. Now remember that this 6 plus, this oxidation number 6 plus, or plus 6, oxidation number of sulfur plus 6, is not an ion. Okay, it's just a way of balancing up where the electrons are. So we can have half equations. It shows whether something is being oxidized or reduced, e.g. iron being oxidized to iron 3 or iron 2 to iron 3. So Fe2 plus becomes Fe3 plus, but what would it have had to have done? Yes, I hear you say it's lost an electron, Nick. Yes, it has. It's lost an electron. So it must have lost an electron to make sure that the iron 2 plus has become iron 3 plus. So writing half equations, usually quite easy, except when we get to some that involve oxygen or hydrogen. Okay, and we're going to go through that in the session. You can write half equations to represent both the oxidation and reduction process. So oxidation is loss, so electrons are going to appear as products, and reduction is gain, so they'll become as the reactants. So Mg2 plus 2 electrons. 2 plus 2 electrons makes copper. Okay, that was pretty straightforward. So now we can use oxidation numbers. Potassium manganate is an oxidizing agent. In acidic solution, it's reduced to manganese 2 salt. So here we have this. Okay, so we've got MnO4 minus and Mn2 plus. Okay, it's not balanced. Okay, well, there's not enough oxygens, are there, for a start? Okay, and the atoms and the charges aren't balanced. So we've got -1 on the left-hand side, but +2 on the right-hand side. That can't work. So here is the process of balancing it using oxidation numbers. Balance the element that changes oxidation state and any other non-hydrogen or oxygen elements. So leave hydrogen oxygen at the end. So Mn, okay, so Mn is O4 minus, so 4 minus, 4 lots of 2 minus is 8 minus. The Mn must be +7. Okay, work out the oxidation of the element that's changing to oxidation state. So here MnO4 is changing, it's going from +2 to +7 to +2. Okay, so it's reduced and you need to gain 5 electrons. So we have to put the electrons on the left-hand side. We have to add them to the manganese, which is in this current state +7. And that balances. Okay, that's cool. Right, now we need to balance the charge with hydrogen ions or hydroxide if it's an alkaline system. So you might be told whether it's going to be balanced in an acidic way or a alkaline way. Okay, so on the left-hand side, you count it up. We've got the MnO4 ion, which is -1, plus we've got 5 electrons, which makes it -6 overall. So therefore, we need to add, the reactants are -6, okay, but the products are +2. So the difference is +4. So we have to, sorry, the difference is 8. So we need to add 8 hydrogens, okay? So that means that we've got rid of the 6 negative charges, then we've added another 2. So we've got 2 plus on the left-hand side and 2 plus on the right-hand side. So that is now balanced in terms of charge. And now we have to balance up the hydrogen. Now the way to do that is to add water. So we've got 8H plus, so we must end up with 4H2O on the right-hand side. And guess what happens? Yep, that's right, the oxygens balance as well. And double check, you can obviously double check that all the atoms and charges are balanced. Okay, so that is the half equation for the the MnO4 minus Mn2 plus system. Okay, so how about another example? Ooh, nice one. Cr2O72 minus becomes Cr3 plus. Again, not balanced. Okay, first off, balance the element that changes oxidation state. Well, the chromium is obviously changing oxidation state. It's become +3 from +6. So to balance that, we need to write it out. And notice we've got 2 chromium ions in our compound ion. So therefore, we need to have 2 Cr3 plus made. Okay, work out the oxidation numbers. Okay, so it is going from +6 to +3. Okay, it's reduced. 3 electrons are gained per chromium. So that means we need to add 6 electrons in total because we need to get both of them down to +3. So they're being reduced. So we can pop that in. Okay, now balance the charge with the hydrogen ions, H+ ions. So we've got -2, -6, -8 in total on the left-hand side, and we've got +3 on the right-hand side. So therefore, the reactants are -8, the products are +6. The difference between that is 14. Okay, so 14 is our H+. So we've got Cr2O72 minus plus 14H plus 6 electrons makes the chromium 3+. 2 lots of it. Okay, so therefore what we need to do is finally balance up the hydrogen with H2O. So we need to put H2 on the other side. We've got 14 hydrogens, so we get 7 waters. Yeah. Okay, and then we've got 7 oxygens. Look at that, 7 oxygens, 7 oxygens. We're now totally balanced, and we've got our half equation for the dichromate ion. And obviously that's quite an important one because it's one that we use with the oxidation of alcohols. Okay, so we can double check. We've got 2 chromiums, 2 chromiums. We've got 7 oxygens, 7 oxygens, 14 hydrogens, 14 on the other side as well. And we've also got 2 minus, 14 plus, so that's 12 plus, 6 minus, okay, from 12 plus gives us 6 plus. And on the other side, we've got 2 lots of 3 plus, which is also 6 plus. Okay, so now it's your turn. Okay, so have a go at balancing these. Okay, so let's bring up my little sign. Okay, so balance those half equations. So stop the video now, carry on when ready. Okay. Here we are. Here, check your answers. Check that you get those answers there. Okay, so let's just put up a little sign. If you just stop the video and check your answers. So stop the video and check your answers. Whoa, change the size. There we go. Stop the video and carry on when ready. Let's make that a bit smaller. Nice. Okay. Right. Okay. So if we had an alkaline solution, okay, yeah, we need to balance it that way. We can balance it slightly differently. For instance, yeah, how could we balance this? Yeah. H2 becoming H2O. Okay, we've got 0 and it becomes +1. Okay, so it needs to get rid of 2 electrons, yeah, because there's 2 hydrogen atoms in the molecule of H2. So that is our, how we've done that. We'll now need to balance it with OH minus, won't we? So on the right-hand side here, we've got 2 electrons. So we need 2 OH minus on this side. So now we have balanced that. Okay, balance the hydrogen with H2O. So we have H2 here, we've got another 2 hydrogens here. We only had 1 H2O there, so we need to double it, so we've got 2 H2O. That is now the balanced one, and we can double check the atoms and charges are balanced. We've got 2 negatives here, 2 negatives here, we've got 2 hydrogens, and another 2 makes 4, and 4 there. 2 oxygens, 2 oxygens, so it's all balanced up nicely. So here, basically, we've used alkaline, or we use alkaline to balance the equation, and that is the redox equation for hydrogen. Okay. Let's try it now with this one. Okay, so you can try balancing with that one up, and again, you're going to use. Let's bring yeah, there we go. So you can stop the video and carry on when you're ready. Okay. So balance the elements, charges, state. So the O2 minus does that. So work out the oxidation. So yeah, so we need to make that 2OH minus because we had 2 oxygens here. Look at the oxidation numbers. So oxygen is 0. Now it's -2, but times 2. Add electrons to show how many are lost or gained. So we've lost 4 electrons because we made 2 O negative ions. Okay, so we can put that down there. Okay, and now balance the charge with OH minus. So we have got 4 electrons here, so it's 4 minus on the left hand side, but it's only 2 minus on the right hand side. We need to add 2 hydroxides. Okay, so we need to add 2 hydroxides to the right hand side, so therefore we get O2 plus 4 electrons makes 4 OH minus. Okay, now balance up the hydrogen because we haven't got any hydrogen on the left hand side. We need to balance that up. Okay, we've got 4 hydrogens here, so we need to add 2 lots of water. There we go. So 2H2O plus O2 makes 4 electrons plus 4 OH minus. Okay, now why are those last two equations really important? Well, okay, although in my opinion I don't think it's necessarily going to take off, the possibility is that we might be using hydrogen to fuel our vehicles. Also, we will be probably trying to use hydrogen to in boilers, but then we'd just be burning it. But we can use a system with hydrogen and oxygen, because we've got this half equation for the oxygen, we had the previous half equation for hydrogen. So if we can, use that, we can actually produce electricity from that, and therefore, obviously, that has its benefits, and that's what happens in a hydrogen fuel cell, which would be used in some vehicles. So they are trialing using hydrogen fuels because obviously we want to try and get off of fossil fuels. Okay. The issue I have with that, though, is, of course, where do you get hydrogen from? And the way they generally make their hydrogen is from methane gas, which comes from fossil fuel production. Okay. So what we now can do, and then obviously in the hydrogen fuel cell, we would combine the half equations to produce a system where one thing is oxidized and one thing is reduced. Okay, so we can combine them, and the final equation will not contain electrons, so it must balance. Okay, so you need to probably multiply one of the equations by a whole number to get your electrons to balance, or even a half number, a fractional number. Okay, so for example, iron 2 reacting with manganate. So iron is oxidized to iron 3, so we have that half equation. Manganese is reduced to Mn2 plus, so we have that half equation which we went through previously. How are we going to put those two together? Well, this one needs to get rid of electrons, and this one needs to gain electrons. This one needs to gain 5 electrons. This one just loses 1. So what we would do is we would multiply this equation by the number of equations this one needs to get. So 5, yeah, so we need to multiply this one by 5. Okay, so we combine the two halves. So first off, multiply this one by 5, okay, because we need 5 electrons, okay. And then, okay, so we have it like this. So we've got the two equations. The reduction is this, because this is becoming, so it's gone from +7 to +2, so it's being reduced. This has gone from +2 to +3, this is being oxidized. We've got the electrons, right? Now we can bind them back together. So we put the left-hand side of this one in the equation. We put the right-hand side of this one, the left-hand side of this one in the equation. So put the two left-hand sides together and put the two right-hand sides together. And therefore you can see that the electrons, there's 5 electrons on both sides, they cancel. And then we have our final redox equation. It does contain H+. Where are we going to get H+ from? Well, this reaction is going to need to be acid catalyzed. Okay, so we could get that from sulfuric acid. Okay, so without it, no reaction would take place. It is in potential. We need it in the reaction. Okay, so we need H+. We need acid conditions. Okay, yeah. Okay. Right, so we can full equation for reaction. Find the equation for the reaction of iron 3 with iodide ions. So two reactions are these. Okay. Okay, so what I'm going to do is I'm going to put the message up. You can stop the thing and see if you can work it out yourself. Okay, so you've got the number of electrons. It works exactly the same as manganese. So stop the video, carry on when you're ready. Okay, so how do you put them together? We need iron 3 and iodide as reactants. So equation B must be reversed. Yeah, because you can see here, these two, the electrons are on the same side. So we need to reverse equation B. So we need to have 2I minus becomes I2 plus 2 electrons. So we can only put iodide with iron 3 plus, okay? Or we could put iodine with iron 2 plus. So we can, let's do it this way around. So we're going to reverse B first. So we have a new equation, C. Okay, so yeah, probably, it didn't make a lot of sense trying to do it yourself. Well, you could have tried to do it yourself. It should work. Okay, there we go. Okay, so let's balance the electrons. So to balance the electrons, we've got to multiply equation A by 2 to give D. Okay, so now we've got 2 electrons, and we already had 2 electrons in C. So now we can put them together. So we put the left-hand side together, and the right hand side together, leave out the electrons because we know we've already balanced them. We know we've got 2 electrons on the left and 2 electrons on the right, and they therefore cancel. So yeah, so they've obviously cancelled out in that equation there. So again, now let's have another go with you working on yourselves, and put the little note up. Okay, so please stop the video, carry on when ready. Okay. So, and let's put these up. And I'll put the sign up. You can again stop the video to check your answers. So, whoa. Stop the video, carry on when ready. Okay, so check your answers. Okay, so you've done that, great. Okay, and you got more right, I'm sure. Right, so we can construct a redox equation using oxidation numbers. Hydronide is oxidized to iodine by concentrated sulfuric acid, which is reduced to H2S. So here is, the equation. So we've got the equation this time. And what we're going to do is we're going to go backwards and make the redox equations, so half equations. So H and O can be sorted out later, but we need to balance the I. Okay, so first off, we've got that balanced. Okay, so 2HI because we've got I2. Okay, identify the changes. So we've got the sulfur has gone from +2 to -2. It's been reduced by -8, so it's gained 8 electrons. And if we look at the iodine is -1 on the left-hand side and it's 0 on the right-hand side. So we've got 2 iodides becoming 1 molecule of iodine, which has got 2 iodine atoms in it. So we've gone from 2 lots of -1 to 0, 2 lots of 0. So we lost 2 electrons. Balance the oxidation number changes. So we need to multiply the hydrogen iodide by 4, okay, to, because we had the balance is 8 to 2, so we've got to multiply by 4. So 4 lots of the iodide bit, yeah, and 4 lots here, yeah. So 4 times 2 is 8, and obviously 4 times 1 is 4. Okay, and that works. Okay, so we've got that. Check if anything else needs balancing. We can add H plus, we could add OH minus, or we could add H2O. Okay, so we needed to add 4 waters because we have got 8 hydrogens here. Okay, those 2 hydrogens there are accounted for here, but we still got 8 hydrogens, so we need to add 4 hydrogens. Now we need to check then that the oxygens work. So we've got 4 oxygens here. Yes, we've got 4 oxygens in the sulfate. So right. Squares. Okay, so what I will do is I will find the redox quiz and send it to you. Okay, so you can have a go at the redox quiz, and here are the answers. Okay, obviously. Okay, so that is it for 23.1, and look forward to seeing you in 23.2.